Today we're going to take a look at section 3.3. So our book takes each of our operations separately. So in 3.2 we did addition of whole numbers. Now we're going to do subtraction of whole numbers, and before you know it, we're going to move on to multiplication and then division. So a lot of what we're going to do is going to feel quite similar in structure of the lesson because of that, is that we're just using a different operation and a lot of the same things over and over again. So to start with, a definition of subtraction. Subtraction of whole numbers says, for any whole numbers a and b, where a is bigger than b or equal to, but greater than or equal to b, a minus b is the unique whole number c, such that b plus c is equal to a. And if I use numbers, you'll be like, oh yeah, that's what we mean by that. For example, 4 is bigger than or equal to 1. Because if I take the number 1, there's something I can add to it to get 4. Right? That's it. Okay? And subtraction is one of those things that occurs second. And for kids who have their addition facts really strongly down, subtraction is a very natural reversing of a process. And so you can establish that from this perspective, right? So how does a child learn, that 7 minus 2 is 5? Well, oftentimes people ask them, well, what do you have to add to 5? What do you have to add to 2 to get to 7? And somebody says, oh, yeah, it's 5, right? So that's the definition for subtraction that we use. The next thing we're going to take a look at is, I think it's 3. Yeah, 3 different models for subtraction. A lot of people like the first model. It's the one that seems most prevalent, perhaps. It's called the takeaway model. In fact, if you were to ask most children, what does subtraction mean? They probably would say takeaway, right? It's a very common strategy, or not strategy, but model. So here's an example of a problem that uses subtraction, and they're using a takeaway model for subtraction. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So in this model, you have something and you are physically taking it away. I have this, I'm removing it. I have this, I'm removing it, okay? So as you're taking a look at this, we're going to draw out a diagram for one way to represent this. And so this is a concrete diagram. But we're going to draw our 24 rocks, okay? Okay, so I think I have 24. So I have my 24 rocks, and then with the takeaway model, I have them already, and then I'm going to remove something. In this case, I'm going to remove how many of them? 5, right? I'm going to remove 5 of them. So here are, no, that's 4. Do it again. Well, there we go. There's 5 of them. I'm going to take 5 of them away. If I take a look at what I'm left with, how many am I left with? 19. And anytime we work with units, we were going to include them, context problems. This one has context, so it's 19 rocks. I have it and I take something away. The next model is not takeaway. It's called missing add-ins. So the missing add-ins model talks about needing something and having only a portion of it already. That's what the missing add-ins model is. It's not having it and somebody taking it away. It's needing it and not having quite enough. So there's an example. Lalisa needs to collect 10 leaves for a school project. She and Temes can go out and find 8 leaves. How many more leaves does Lalisa need? Okay, so I don't start with a picture of 10 leaves because she didn't have 10 leaves. How many leaves does she have? 8. So we're going to draw 8 leaves. Okay, so those are her 8 leaves that she has. And then what we do in this model to show what we need is we actually draw the other missing, if you will, leaves, the ones we don't have, to fill up the need of having 10. So if I fill this in, I use these dotted ones to represent this, so feel free to do so in like a lighter color or something like that if you wish, or dotted. But those pieces are what's missing. And if I were to consider all of these together, it'd be the 10 that I want. And then the answer to the question is how many are the missing ones? And so how many are missing? 2. So she needs 2 leaves. And an algebra type of an equation, what you can actually write down, and you will see this a lot in current curriculums, is missing spots with a blank. 8 plus blank equals 10. And so they're wanting the child to fill it in, and of course this one would be filled in with the number 2, and 2 would be my answer. The thing that you have to be careful, or I don't say careful about, the thing that I want to make emphasis to you about is this equation kind of perspective is taught at a much younger age than you remember it being taught. So some of you, even now, some of my students all over OBU, even now, use equals to mean and the next step is, and the next step is, and the next step is. And some of you, Brooklyn's up here nodding. We do that a lot, don't we? It equals means and the next step is, but it actually doesn't mean that. It means 2 sides that are both equal in value. And so they're trying to sort of ingrain that idea at a much younger age that an equal sign means 2 sides equal in value. So you see this kind of an equation, doesn't have variables in it, but this kind of an equation showing up as early as 1st and 2nd grade. Yeah. So just be aware of that it's not algebra, but it's actually setting up the stage for algebra later on, and so that's a little bit more of a familiar idea. Okay, so we have takeaway, we have missing add-ins, and the third one we have is called comparison. So the comparison, I'm sorry, your book doesn't do comparison anymore. Comparison is the one that they decided to drop. You don't know why. Number line is the one they kept. Okay, so number line, the measurement model. So sorry. The number line model talks about taking the same kind of ideas that takeaway and missing add-ins have, but they do it for something that you can measure, right? I don't measure the size of the leaves. I don't measure how big they are. I'm not measuring them, right? I'm just counting them. But when we're working with measurement, we're talking about something that has a certain length. Now, we're still working with whole numbers, so we're talking about whole miles in this case, or we're talking about whole cups if you were doing cups of, flour or something like that. So you're still talking about the object without any decimals, but we're looking at something that has a decimal expression that actually makes sense. Like I can have 1.5 miles, right? I can have 1.5 cups of flour. I can't have 1.5 leaves and that makes sense for the project, or 1.5 rocks. So this is an example of a measurement model. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls and asks him where he is. He states he's coming home and he has driven 8 miles so far. How far is Akeem from home? So with a number line model, you can actually draw a number line model picture. So we start at home. That's my home. Just like that. It doesn't look like a very nice home. I was wanting to do a window. That's a little bit better. There's home. And then we've got the mall. Right? So this looks like the city, but there's a mall over there. That's the mall. Okay? And how far apart does it say that home and the mall are? They're 15 miles. And then Akeem gets a phone call on the way home. And how far has he driven home when he gets his phone call? 8 miles. So he's back here at maybe right here. So this distance so far that he has come back towards home is 8 miles. And then the question is how much remains for him to drive? And how much would remain? It would be 7. And this particular type of a diagram even feels very much like the definition that we started with over here. What piece do I have to add to get to the total 15, right? And again, it also feels like my leaves question. What piece do I have to add to get the total 10? So this is a number line model. It definitely is because I'm talking about miles. But it's got that missing add-in sort of perspective to it as well. I've got this missing piece. All right, so here's what I would like for you to do now. 1, 2, we've got 4, 14. Okay, I'm not going to have you move just yet. Okay, so turn to a neighbor real quick, just where you are. I'm going to put you in groups later, but I don't even know if we'll get to that today, so I don't want to move you all for that 3 problems I've got right here. So turn to a neighbor where you are right now, so you guys can pair up and pair up. And then if Kira and Brenna maybe back at the back, and then just kind of come across through the middle right here. And then if Brooklyn, you'll just move over here with Teresita, then I've got pairs. We've got an even number of people. What I want for you and your partner to do is I want you to create an example of each of our 3 models. Okay, your word's a word problem. You're going to write a word problem. Doesn't need big numbers, doesn't need to be complicated. You don't even need to solve it. You're just writing the word problem. 1 for takeaway, 1 for missing add-ins, and 1 for the number line or measurement model. All right, so I'm going to ask you guys to give us an example of ones you picked, okay? So the first one I'm going to start with is takeaway, and I'd like 3 groups to tell us. Once your group talks, that's it. You're only going to share 1, or we'll be here for a little too long. So somebody share a takeaway model that you have. Abigail.
Sally had 12 cookies. Her brother ate 5. How many does Sally have now?
All right. Somebody started with food examples there. Okay. 12 cookies and her brother ate 5. That is definitely a takeaway model. Okay, who wants to share another one? Ashley.
So John had 30 worms and a bird ate 12 of them. How many does he have left?
So this is sort of a food example. I mean, it's food for the bird. Did you think of the worms because the worms were all over the ground this morning? That's what my daughter noticed. There were worms everywhere. Okay.
So John was supposed to be my teacher.
Oh, I see. Okay, so tell me your numbers again. What did you have?
30 and 12.
30 and 12. So she had 30 worms, and then 12 of them were eaten, right? Cool. All right, so that's definitely a takeaway model. One more example of a takeaway model. Brenna.
Kate has 6 soccer balls and lost 2 at practice. How many does Kate have?
Awesome. So she had 6 soccer balls, lost 2 at practice. Definitely something that can happen when you play soccer. I've seen this, yes. This is why my husband has like 15 soccer balls, as he coached soccer, and he just decided he needed to buy a whole bunch of them. Yeah. All right, cool. All right, how about missing add-ins? If your group's already spoken, please let other groups speak this time, okay? So 2 of them for missing add-ins. Teresita.
It says Beth is making a cake. She has 2 cups of flour, but to make the cake, the recipe requires 6 cups of flour. How many more cups does Beth need?
Awesome. So we've got a missing add-ins model. She needs a certain number of cups of flour, and she only has so many of them. And she's probably going to go to her neighbor and borrow them, right? Probably so. I mean, she's not going to really get them back, so it's not borrowing, but people say it all the time. Kayla.
Okay. Dr. Hands needs to collect 14 redos, but she only has 5 redos. How many more redos does she need?
There you go. I need to collect 14, and I only have 5.
Yes.
That is unfortunate, isn't it? Indeed. Very unfortunate. Okay, so whoever hasn't spoken, there should be 2 groups. Someone tell me what your number line measurement model was that you gave your example to be. Brooklyn, Blessing, one of you want to speak for me? Did you guys do one already? I don't think so, right?
No, we haven't, but we haven't finished the thing. Okay.
Well, tell me how you think it'll finish.
Okay. You got it? Okay. Me? Okay. Sean drives 15 miles to visit Brittany. Blessing calls him to tell him to pick up a pizza. Sean is 5 miles from OBU. How far is he from what? I was like, honestly, I haven't finished.
All right, okay. So, but your idea is that he's driven, so if he's driven or ridden so far, and then he's going to stop. And one of the things you want to be careful if you're going to create a problem like that is that he's using the same path there and back, so that your same number of miles fits. Because if you think about it, you can definitely go out of your way to a pizza place on the way back. So you just want to be careful when you're structuring it. But that'll work. Yeah, okay. That would be the idea. Good. Who else is not gone? All right, up here up front. What do you have?
So I have Summer is walking from her room to the pool, which is a 10-minute walk. Halfway there, she realizes she forgot her water bottle. How long will it take Summer to go back to her room?
Okay, so the only thing about that one is that once you said halfway there, you're almost doing a multiplication or division type problem. So you want to be careful and say 5 minutes instead. That'd be great. Yeah, and that's a good example because you used one that wasn't miles, and so minutes works too, right? Because you can take a portion of minutes. I heard you guys talk about minutes over here too. Yeah, so minutes is another one of those things that's a measurement value, so that would work really well. And in fact, the one that you guys did with flour up here, you could use for a measurement model as well because you're measuring cups, and cups is a measurement. So, all right. Let's take a look then, and you can shift back to seats if you've moved and you'd like to. So a few more things in our section before we're done today. Some properties. So we talked about properties of addition. You had the closure property, the commutative property, the associative property, and the distributive property, right? There were 4 properties of addition. And we're going to take a look at those same 4 properties and see which of them hold for subtraction. So the first one example is closure. Does subtraction have a closure property? Is it closed with respect to subtraction? So remember, the closure property says, can I take any 2 numbers, in this case whole numbers, because I'm asking about whole numbers, and subtract them and get another whole number? No. Can you give me an example?
If you do like 5 minus 2, negative 2, so.
Okay, so 5 minus 2 would work because it's actually 3. But if you did 5 minus 7, yes, I'm with you. Yeah, so this one's not a whole number. So some of the time we do get whole numbers when we subtract, and some of the time we don't. The ones that we do for, I mean, that's great, but it has to work all the time, and it doesn't work all the time. So the answer here is no. There's no closure property for subtraction. How about commutative? Can you give me an example, Brooklyn?
Well, 7 minus 3 is not the same as 3 minus 7.
Good. 7 minus 3 does not equal 3 minus 7. The order of subtraction matters, right? It really does. So there's no commutativity for subtraction. I'm going to burst your bubble right away and tell you associative doesn't work either. So I'm going to give you an example just because it's a little bit easier for me to construct this one probably than you guys. If I took 3 minus 2 and then I subtract 1, or if I do 3 minus and then I do the 2 minus 1 like this, let's work from the inside out. So 3 minus 2 would be 1, and 1 minus 1 would be 0. Over here, 2 minus 1, inside the parentheses, is 1, and then 3 minus 1 is 2. And of course, these two are not equal. So no associative property for subtraction. And identity. Yeah, I mentioned that wrong. I said distributive. We aren't at distributive yet. We'll get that next time. Identity property, you had an identity property for addition. What was your identity element? What was the number? 0, right? Because if I add 0 to anything, then it doesn't change the value, so it's the identity element, which is what gives me the identity property. Is there a number like that for subtraction?
You can subtract 0.
Okay, so let me use 6. 6 minus 0, that one's 6, and that works. Is that all that has to work for it to be an identity? What has to also be true? Any idea?
Yeah, 0 minus 6.
This one would also have to work, and it's negative 6, and that's a fail. So there is no identity as well. If we had such a thing as like a half identity, this would be it. But that's not a thing, right? It isn't. So we do not have an identity element for subtraction. So the next thing we're going to move into is some algorithms for subtraction. I think I can get through all 4 of the algorithms before we quit, and then we'll pick up on other bases next time. So our first subtraction algorithm is the concrete model. You've seen the concrete model before with addition. In fact, we used almost the same example. We used 34 plus 18, and now we're going to use 34 minus 18. So the subtraction algorithm says that I'm going to draw my 3 longs and my 4 units. So there's 2 longs, 3 longs, and I have 4 units. Okay, so that's the number 34. And then the subtraction algorithm is like a takeaway kind of perspective. I'm physically going to be removing something that I already have. So imagine having these, as Lego stacks or something like that. Well, I can take away 4, and I can take away a 1 long and 4 units pretty easily, but I need to take away 1 long and 8 units. So what would I have to do in order to take 18 away when I only have 4 individuals that are there? What do I need to do?
Break up 1 long into 10 individual.
Exactly. I need to break up one of my longs into 10 individual units. So I'm going to change the diagram. And so instead of the diagram having 3 longs, I want it to have, oops, that's not what I meant to do. Try it again. I want it to have 2 longs. And instead of just having 4 individual units here, it'll have those same 4, but it needs to have 10 more. Okay, so there's my 10 individual units with the 4 units there. It's still the same number. It's still 34. But it's in a form that I can actually take some things away. So I can physically remove 8 of these guys, any 8 I want, and 1 of these guys. And if I do that, what am I going to be left with? How many longs? 1 long. And how many units? 6. And the number would then be 16. So you can do this really nicely with like Legos. Legos would be a great way to do this because you can physically bust them apart. Even if I bring in, which I will at some point and remember to bring my base 10 blocks in, they don't have the ability to actually snap apart. I would have to actually take a long and I'd have to exchange it for the units. So Legos is actually a better way to do this, or a base 10 blocks that has the ability to snap things together are even better than my base 10 blocks. But this is the idea, so you can physically see what's happening. Now, the next algorithm is the one that you know and love, called the standard algorithm. The standard algorithm did something we probably all have called borrowing before. You use the word borrowing? Okay, me too. If you use it with a 4th or 5th grader now, or maybe even younger, they're probably not going to know what you're talking about because that's not the language that's currently used. They use the word regrouping, just like we used the word carrying, and I told you we use the word regrouping. So regrouping is the idea of moving things or shifting things around so that you can do the subtraction within the columns where they are. It's the same thing as the borrowing or the carrying that you used to do. It's just more accurate language for the mathematical process. So when we're looking at 4 minus 8, because with the standard algorithm we start in the right-hand column, we say I don't have enough. Okay, so what we would have said is I need to borrow, and what they would say is they need to regroup. So they're going to take this 3 and they're going to take and put it a 2 there, and they're going to regroup that number 1 that was really the number 10 by associating it with the number 4. They might write it as a 14 like that, or they might write it with a 1 right there beside the 4. Either way I've seen used, so that's sort of negotiable. But either way, I have regrouped one of my 10s into the 1s column so that I now have 14 1s, and I can subtract, giving me a 6, and then the 2 minus 1 giving me a 1. So I'm regrouping. The expanded algorithm, just like when we did addition, does the same thing. It just does it in a little bit more visible way. So I write this as 30 plus 4 and 10 plus 8. And I'm subtracting, so when I do my subtraction, it's going to change this into a negative 10 and a negative 8. I'm subtracting both pieces, if you will. Okay? So just like with the standard algorithm, I don't have enough within the individual columns to do the subtraction, so I need to regroup. So I take the number 30 and I regroup 10 of those numbers over here with the number 4 to give me a 14. And then I can actually move from left to right or right to left because I have enough in each column to do the subtraction. So if you wish it, you can write a 10 here, you can write your 6 here, and it's addition now because the components were originally added together. We've done our subtraction so that we get a 16. Give me 1 minute and we'll be able to finish the last example, okay? We had an algorithm called opposite change. Y'all remember that one? Where we added a number and we subtracted a number equally across and we just compensated. Equal additions is the same algorithm, but it's for subtraction. So if I'm going to subtract and I stack them up, the idea again is I want zeros. But very specifically here, I want zeros in the bottom number now. Before with addition, I don't care where the zeros are. It makes the addition easy either way. But here it matters. I want the zeros to be on the bottom. So in particular, for example, I can add a 2 to 158 and I will get 160, which is a more pleasant number because it has a 0 in it at the end. But when I was doing the opposite change, I had to affect the other number in the opposite way. Here, I affect them in the same way. It is an equals addition algorithm. And the reason is because I am, in fact, subtracting. Right? It's just like if you and I were both standing next to each other when we said, oh, look, we're 2 inches apart in height, and then we both put on 3-inch heels, we would still be 2 inches apart in height because we added 3 inches to each of our heights, right? So this is now 836. So that's good. I mean, I've got the 0 in one of the places. But again, you see the 3 and the 6, that's no good because I still would need to borrow. So the whole goal of this algorithm is no borrowing. And we do that by getting zeros or creating zeros. For example, 160, I'd really like a 0 where that 6 is. So what could I add to it to make that happen? 40. And if I add 40 to the bottom, I have to add 40 to the top. This is 876 on top. And what is it on bottom? 200. Then I can subtract without any borrowing, and I get 676. And we will pick back up with the other bases next time.